Before we watch this video, you should already understand the different types of loads that can be applied to an object, including support reactions. And what this video covers is creating free body diagrams from an object, the information you have about an object and the loads applied, and using that to write equilibrium equations, which can be used then to solve for support reactions. So, and these apply, we can use these when there's no acceleration, that is no linear acceleration or angular acceleration, so the object is not speeding up the direction it moves or speeding up its rotation. And this situation includes when an object is simply at rest. That's the most common situation for the equilibrium equations to apply. And so in this case, we have support reactions that prevent movement or rotation, and we're calculating what or we have supports that prevent that, and we're calculating what the support reactions are there. So our steps to use free body diagrams and equilibrium equations, you can look at this as abbreviated DICES, is that you draw a free body diagram of the object, and you want to on this indicate any information you have about distances, angles of interest, and do these whether they're unknown or known. Then you want to indicate the external forces and moments on the object or acting on it, including unknown support reactions for which you might have to interpret wording or information into those support reaction cartoons. Then you want to, the C is to clarify knowns and unknowns. This helps you know what you're trying to solve for. And then you can write the equilibrium equations. And clarifying the unknowns is very helpful because you expect to have one equilibrium equation for every other unknown in order to solve for all the unknowns. And I should mention these are one linearly independent, sorry, that shouldn't say interdependent. Whoops. Let me fix that. One independent equation. And so in a two-dimensional problem, you only have equilibrium equations for rotation and the movement in the two directions, and so generally you want at most two unknowns, whereas in 6D you might have 6 unknowns to be a well-determined problem. So then after you've written the equations, you just solve the unknowns. At this point you're just down to math. You've already had to do the hard mechanics conceptual work. And then lastly, you error check your answer. And error checking your answer is a very simple step. You might have intuition about sign and magnitude. You always want to, when you error check, the one thing you always want to check is your units to make sure your units are in the units of force or moments. So newtons for force and Newton meters for moments for the things that you've calculated. And finally, you can plug your answer back into the equilibrium equations to make sure that they work there. So how do we write the equilibrium equations is our next question. And we use the fact that all the forces and moments sum to 0 for an object when it's at equilibrium. And I mentioned before the numbers of equations we're solving for. So the equilibrium equation for force, what we start with is if we have any forces that are not on the orthogonal axis, for example, we might use the x and y axis. Any forces that aren't on those, we decompose them. And if you remember, for example, if you want the force in the x direction of a force that goes in the theta direction, so theta sub f is the direction of the force, the f component is x cosine theta sub f, if theta sub f is the angle relative to the x-axis. So here's x, and there is theta sub x, and then that leads to the x component of that being the cosine of theta f times that magnitude. So you want to make sure you include all forces, known forces and support reactions applied to an object. If you have distributed forces, you can replace them with the resultant force first or use the entire distributed force, put it in the diagram. But it's usually easier to break down your problem by calculating that resultant force first and the location and putting it there. And then also keep in mind, this may be new to students in my class, when you write your force equations, even if there were external moments on that, they do not contribute to the equilibrium equations for forces. So next, you're going to write the equilibrium equations for moments. So again, you want to include all moments, known and support reactions applied anywhere on the object. And now you have this step, and you don't have any of that decomposition problem that you had for the force equilibrium equations. But you have another step, which is to select an origin around which you're going to calculate moments. So if they're external moments, pure moments, like we've talked about in a previous video, they're the same no matter where you find your origin. Just like the impact of forces is the same no matter where they are applied, they just add up. But we're also going to have this issue that all forces contribute a moment unless they point through the origin or away from the origin. So if they're aligned with the origin, they don't create a moment. Any other situation, they create a moment. So that makes it that your moment equations will look different when you pick different origins, and you'll get different equations, but you should get the same final result, although some of the choices will involve a lot more calculations than others. And that is an art you will learn to do about selecting origins. But no origin is wrong, just some of them are harder. So one note that I like to set the origin at the location of an unknown force. And that way that unknown force doesn't contribute to the moment equation. It will still show up, that unknown force will still show up in the force equations, but it often allows me to solve for unknowns a little bit more one at a time instead of having a lot of basically a linear set of linear equations that I have to manipulate and combine equations to solve for. I'd like to solve one and exchange into the other and exchange into another. It makes fewer calculations than if I have more than one unknown in every equation. And also note that we can use more than one moment equation, but your equation set will be redundant. They will not be independent. You'll have some that are dependent on others, or effectively a remanipulation of your other three equations. So here's our summary of the unit on free body diagrams. So we learned the following types of loads can be applied to an object: concentrated forces, couples or moments, and distributed loads, which can be replaced by a resultant load. And we talked about these in distributed forces. Later in the quarter, we will talk about distributed moments. And then we also learned that unknown support reaction arise from context with things that restrict the movement. We can have fixed supports that had 3 unknowns, pins or hinges that have 2 unknowns, and cables or rollers that have one force, although in the case of actually both cases, if your cable's at an angle, but if the things are at an angle, you might decompose, but there's only one unknown because theta is known. So then we learned how to use the equilibrium equations to solve for the unknown support reactions, using the fact that forces in each direction sum to 0, and the moments along any axis sub to 0 in the xy plane. Rotation in the xy plane is around the z-axis, so it's called m sub z. And we learned that only forces contribute to a force equation, whereas forces times the distance from the origin, as well as moments, contribute to the moment equation. I should have said cross product, not times. So we learned how to write those moment equations, and we learned that you need one independent equilibrium equation per unknown. and that moment equations on different points of the object combined with those force equations may not be independent. So that was our lesson, with a big emphasis on the new materials being, I believe, the support reactions and the equations regarding moments.